Forces are acting on an aircraft during flight. Now we will see all the four forces acting on an aircraft separately. Let us discuss lift first. What is lift? What you are seeing is a cross-section of a wing. The shape is an airfoil. The airfoil shape has a curved upper surface. Due to the curved upper surface, the air flowing above the wing has to travel more distance than the bottom surface, which is flat. Air flowing above the wing has to travel faster to catch up with the air flowing below the wing. As per Bernoulli's principle, due to the increase in airspeed, the pressure decreases at the top of the wing. Comparatively, the bottom of the wing has a higher pressure. This pressure difference pushes the wing upwards, thus creating the lift. Let us see the Bernoulli's principle in detail. If the air is passed through a straight tube with the same inlet and outlet area, the speed at the outlet will be the same compared to the inlet. Here, the inlet speed is 100 miles per hour and the outlet speed will be the same, 100 miles per hour. Now, we will pass this air through a tube which has a narrow middle. The inlet and outlet area is the same. Here we can see the speed of the air is increased at the middle. The inlet and outlet speed remains the same. Now let us see the pressures. The pressure is the same at the inlet and outlet, but at the throat we can see the pressure is reduced. This happens because the same amount of inlet air should pass through the outlet. So the speed at the throat should increase, which causes a reduction in pressure. But what does this have to do with flying? Let us cut this model in half. We will have a profile similar to an aircraft wing section. I will explain a few more things connected to lift. An imaginary line connecting the leading edge and the trailing edge of an airfoil is called the chord. The airflow striking at the wing is called the relative wind. The angle between the chord and the relative wind is called the angle of attack. Now we will see how angle of attack affects lift. As I explained earlier, the angle of attack is the angle found between the wing, chord and the relative wind. During straight and level flight, the angle of attack of the wing will be low. To climb more, lift is required, so the angle of attack is increased so that the wing can produce more lift. To descend and land, less lift is required, so the angle of attack is reduced. If the angle of attack is increased further, we can see the smooth airflow over the wing is disturbed and starts separating from the surface. The wing starts stalling and loses lift partially. When the angle of attack is increased further, the wing stalls fully and the lift will be completely lost. Stall recovery is possible by reducing the angle of attack.
Now we will see a wing stalling on a smoke tunnel. Here the air is flowing over a cross-section of a wing. Here the angle of attack is normal and the airflow over the wing is also normal. The angle of attack is increasing now. The airflow over the trailing edge starts separating now. When the angle of attack is further increased, airflow over the entire wing is separating. When this happens, the wing stalls. The aircraft will fall like a stone. The stall recovery is possible by reducing the angle of attack.